Welcome to This Explainer. Today, we're taking a deep dive into the absolutely stunning, sometimes totally dark, and honestly sometimes rainbow-colored world of particle physics and mega colliders. We're going to be talking about the massive, mind-boggling machines and the deeply ingenious methods that humans have actually devised to crack open the universe and peek at the fundamental building blocks of reality.
Okay, to really set the stage here, I want you to just take a quick second and look at your thumbnail. Right now. Just glance at it. Consider this absolutely wild fact. At this very second, roughly 100 billion invisible solar neutrinos are passing straight through your thumbnail. I mean, they're streaming in unfathomable numbers through your entire body, and you don't feel a single thing.
And it's not just neutrinos from the sun either. We're all constantly stewing in this invisible particle soup. We're bathed in a rain of muons that are birthed right up in Earth's atmosphere. Even a completely normal banana sitting on your kitchen counter is actively emitting positrons, which is actually the antimatter counterpart to the electron. It's crazy. So this poses our central mystery for today. If we are living in this rich, dynamic, totally invisible world, how do scientists actually see it? How on earth do we capture matter's hidden, beautiful reality?
That brings us to our first main topic, making the invisible visible.
Since we obviously can't just pop a subatomic particle under a regular microscope, we have to look for the tiny little subatomic breadcrumbs they drop as they travel around. As Jennifer Raff, a physicist over at Fermilab, puts it so perfectly, basically every single detector we build is looking for one of three things: light, heat, or electric charge. Scientists build these incredibly intricate, sometimes literally building-sized machines just to capture those fleeting, invisible signals and translate them into a language we can actually understand.
Looking back at how these detectors have evolved, it's pretty much a story of our technology scrambling to catch up with our theories. Back in the 1930s, we had cloud chambers. These were filled with alcohol vapor that was just on the absolute verge of condensing. So when a charged particle zipped through, the vapor would condense right on its path, leaving this wispy little line, kind of like an airplane's contrail. Then, by the 1950s, we upgraded to bubble chambers. When charged particles passed through liquid hydrogen, they'd leave behind these beautiful, sweeping, iridescent spirals of bubbles. And today? Well, today we've moved into the digital age. We're using incredibly advanced scintillators and digital silicon tracking layers that let us instantly record literally millions of collisions every single second.
I have to admit, one of my absolute favorite phenomena in all of physics is Cherenkov light. Think of a supersonic jet, right? When it breaks the sound barrier, it creates a massive sonic boom. Well, light actually slows down when it passes through certain materials, like water. So when a highly energetic particle gets injected into that material and actually moves faster than the localized speed limit of light, it creates a visual sonic boom. It's a vibrant, bright blue flash of Cherenkov light. It's just this beautiful, glowing data point lighting up the dark, proving that a particle was right there.
Which naturally leads us into part 2, CERN's current frontier. So CERN is really the global epicenter for modern particle physics. And wow, in the year 2025, they expanded our knowledge immensely. Just take a look at some of these breakthroughs. They actually demonstrated the very first antimatter quantum bit. They quite literally achieved modern alchemy by converting lead nuclei into gold nuclei. No way, right? We also saw the first ever collisions of oxygen and neon ions at the Large Hadron Collider, which let us probe the deep secrets of the early universe. And all of this incredible work culminated in a record amount of data being delivered just before the LHC Run-3 Proton Physics program officially wrapped up in May of 2026.
But what comes next? Let's talk about building the Future Circular Collider, or the FCC.
Here's the reality. To find entirely new physics, that current 27-kilometer Large Hadron Collider, it's eventually just not going to cut it anymore. We have to look beyond it to a machine on a true planetary scale. We are talking about a massive 91-kilometer circumference ring, resting about 200 meters below the surface of the Earth, stretching all the way across the borders of Switzerland and France.
Now, the really crucial thing to understand here is that this FCC proposal isn't just one giant machine. It's a highly strategic, two-step master plan. Stage 1 is an electron-positron collider. You can kind of think of this as a precision factory. Its main job is to perfectly map out the properties of the Higgs boson. The particle responsible for giving elementary particles their mass right after the Big Bang. Once that delicate precision work is done, Stage 2 kicks in. They'll convert the tunnel into a proton-proton collider operating at a totally unprecedented 100 tera-electron volts of collision energy. So we basically go from a precision scalpel straight to an absolute sledgehammer, shattering energy records to reveal the universe's most stubbornly hidden secrets.
Of course, digging a 91-kilometer tunnel and filling it with ultra-advanced tech doesn't exactly come cheap, right? The estimated cost for just the first stage, including the tunnel and all the infrastructure, is 15 billion Swiss francs. But this massive investment would be distributed over roughly 12 years, starting in the early 2030s. And if we look at history, the technological spin-offs from these megaprojects, stuff ranging from medical imaging and cancer treatments all the way to advanced computing, they pay massive dividends back to global society.
All right, moving on to Section 4, pushing the limits.
What if, instead of just building a bigger ring, we change the actual particles we're colliding? This is where we literally get into rocket science with particles. Take the concept of a muon collider. The protons we currently use in colliders are, well, they're bulky. They're composed of smaller parts called quarks. When you smash protons together, you're really just smashing their messy internal parts, meaning only a fraction of the total energy actually goes into the collision. But muons are point-like particles. They have zero internal structure to worry about. So when you collide a positive and negative muon, 100% of their entire collision energy goes directly into the reaction. Because of this extreme efficiency, you can achieve massive physics results in a much more compact ring.
And that whole rocket science approach, it definitely doesn't stop there. We are also deeply exploring plasma wake field acceleration. Imagine a speedboat tearing across a totally calm lake, leaving a massive wave or wake behind it that a surfer could just ride. Scientists are doing exactly this, but with subatomic particles. They drive a bunch of electrons or protons through a plasma to excite electromagnetic waves. Trailing particles then literally ride these plasma waves, getting propelled like a rocket to massive, unprecedented energies over incredibly short distances. It's basically an ultra-concentrated crash course in high-energy physics.
There is a catch to all this immense power, though. Particles like muons decay super quickly, dropping off an intense shower of background radiation. When scientists look at the simulated tracking layers for a muon collider, they have to design unbelievably sophisticated geometry just to filter out the noise and separate the real, valuable tracks from the beam-induced background. It's an engineering hurdle that's basically akin to trying to hear a single quiet whisper in the middle of a Category 5 hurricane.
Now, you can't just build these next-generation mega machines without a rock-solid socio-ethical blueprint right from the start. It's all about smart, sustainable eco-design. Teams are actively working to keep the environmental footprint as low as possible by developing territorial synergies. For example, they're looking at capturing the immense heat generated by the collider and actually reusing it to warm nearby communities. These massive endeavors rely heavily on global collaboration, making sure that the benefits of this research naturally flow back to improve our everyday lives through things like advanced medical and fusion technologies.
At the end of the day, we are fundamentally chasing shadows in the dark, trying to unlock secrets that the universe tries its absolute hardest to keep hidden from us. So, as we stand on the precipice of these massive new machines and this literal rocket science level of particle acceleration, I want to leave you with this. When we finally smash through that next fundamental boundary, what beautiful, unseen reality are we going to uncover next?